All right, in this video we're going to do example 2. Let's just carefully read the problem together. A farmer has 2,400 feet of fencing and wants to fence off a rectangular field that borders a straight river. He does not need fencing along the river. What are the dimensions that maximize the area of his field? I think for this particular problem, doing a diagram is helpful. So what do we have? We have a width, a length, it's a rectangle, and another width. And here's my river. Right? And here's my grass. This is the area. Okay. So, what do we want to do? And I'm just thinking right now, actually, that I want to change my color scheme a little bit, given the fact that I was using pink for objective function. So how about length? And here's your area. I was thinking green for grass, but I want my objective function there. So let's go ahead and read it again and see what we can identify. A farmer has 2,400 feet of fencing. That's a constraint. He doesn't have more. And he wants to make this rectangle. He doesn't need fencing along the river, so he just needs fencing for a width, a length, and another width. And we want to know the dimensions. In other words, we want to know the length and the width. That are going to go ahead and, oh, there's the word I'm looking for, maximize the area of the field. So I see that word maximize, there's my objective. Okay, so I feel like we understand the problem fairly well. What we want to do is identify our objective function, our constraint function, substitute that constraint into the objective so it's a function of one variable, and then think about domain. Okay, so objective. It is my area. And we know that the area is equal to the length times the width. The constraint is this amount of fencing. So how much fencing does he need to use up? That's a perimeter question. Because he doesn't need fencing along the river, we just need a W plus an L plus a W. W plus an L plus a W. That has to add up to 2,400 feet of fencing. He wants to use, or she wants to use, all of the fencing that they have, because we want to make the biggest possible rectangle for our cattle or our sheepies as possible. So my constraint here, and I think I'll drop my color, is 2W plus L needs to be 2,400. Now at this point, we have an option. We could solve for L, and then we'd have L in terms of W stuff. And so I could come up here into my area function and replace L with W. or we could solve for W. And then substitute in, and then we'll have everything in terms of L. It's really a matter of choice. And let's talk about why one is a little bit better than the other with these particular numbers. If we solved for, oops, I'm ahead of myself. If we solved for W, W would be, dividing that by 2, 12,000 minus L divided by 2. And that would be perfectly fine, in which case area is length times width, and width is right here. Making that substitution, area is length times width. Now, the only reason that I don't want to do this, it's perfectly fine, but here, having a fraction just makes my life a little bit more difficult. Now, if I did work with this and I had area all in terms of L, the domain restriction for L, my L can't be all the fencing. I need some fencing for the width. Right? You know, there's all sorts of possibilities for these rectangles. Maybe the width is really, really, really tiny, and the length of the fence is really, really, really long. Cows probably wouldn't like that. Or maybe they're a little bit more equal to each other, right? But the amount of fencing that I have has to add up to 2,400, and if the length was the entire 2,400, we'd have no fence. So if we were to do this for our domain, 0 would be less than or equal to L, which would be less than or equal to 2,400. All right, so this is a perfectly fine option, but I am instead going to go ahead and solve for L just to not have a fraction here. So L would be 2,400 minus 2W. And I'm going to take that constraint boop, maybe not yellow. I'm going to take this constraint and substitute it into my objective function. So now my objective function will be just in terms of W. Objective. All right. So I'm deciding to not have too much color here. My area is equal to my length times my width. Well, my area is equal to length. Well, what the heck is length? Length is 2,400 minus 2W times W. Maybe I'll draw my arrow this way. Okay. So my area is equal to 2,400 W minus 2W squared. Again, this one does happen to be a parabola, so calculus is a little overkill here, but I want to do this with calculus, A, to use the closed interval method, and then B, to talk to you about, like, what if you weren't able to think about the domain? That's okay. We have some options, okay? So let's actually think about the domain right here, though. So here A is written in terms of W. So what we know, W's got to be bigger than or equal to 0. If the width is 0, you do not have a rectangle at all. Now, because the constraint is 2,400 feet of fencing, if both the W's added up to 2,400, then you would have used up all the fencing on the width, and you'd have no fencing left over for the length. right? So you know that half of that is the biggest W could be, right? If W equals 12,000, 2W is already using up all the fence. All right, so here is my objective function, and here is the domain. Okay, we're going to use the closed interval method to maximize that objective function. Since a is a continuous function, it's a polynomial on a closed interval, what are we going to do? We'll use the closed interval method to find the absolute max and absolute min. It's guaranteed to have it on this domain. Okay, so step 1 is find those critical points. A is equal to this. A prime, oops, I erased a little too much. A prime is equal to 2,400 minus 4W. There are no places where the derivative doesn't exist, right? There are no domain restrictions. So I only have to consider where the first derivative is 0, factoring out a 4. We've got 4 times 6 is 24, so 4 times 600 minus W is equal to 0. So here's my critical point. W equals 600 is our critical point. Now I need to go ahead and evaluate my objective function, my area function at that critical point. Let's do that on another piece of paper. All right, so evaluate A at W equals 600. Okay. Beautiful. Okay, so we're just going to plug in 600. And I've already crunched this here. I got a graphing calculator. Right, so here we have it. Our area is equal to 720,000, and it's an area, so it's units squared. And what is this? Feet? So feet squared. That is a potential absolute extrema. All right, because our function is a continuous function on a closed bounded interval, absolute extrema can also occur at the endpoints. So step 3 is to evaluate my area function at the endpoints. And the domain for, because I wrote area in terms of W and there's 2 widths here, the width has to be something. If the width is 0, we have no area whatsoever. And if the width is 12,000, we also happen to have no area whatsoever. Because 12,000 plus 12,000 is 24,000. I keep saying 1,000, I apologize. 100, 1,200. We would have no fencing left over for our length. When you put in 0, you get 0 minus 0, we get 0. potential absolute extrema. It's me putting in 0. And also when we put in 12,000, we happen to get a 0 as well. Oh my goodness, I said 1,000 again. 1,200. Bloop, bloop. We get 0. So now we just are going to compare. Again, another potential. There we go. We're going to compare. That's an RE. Those values from step 2 and 3, right? Those potential absolute extrema. We can even write them. The 720,000 square feet and the zeros. Clearly, the biggest one here, that's our absolute max area. Okay, now the question didn't ask for what the absolute max area was. It asked for the dimensions. What are the dimensions? So go tell me what W and L need to be, right? And we know W's got to be 600. Let's go find the length. All right, so my length is 2,400 minus 2 times 600. My length is 2,400 minus 1,200. I can't keep track of my zeros. It's 1,200. Okay? So in conclusion, the area is maximized when your width is equal to 600 feet and the length is equal to 1,200 feet. The max area is those two multiplied together. Square feet. All right, now if we look at the graph, right, here is my area function in terms of, I'm writing an X for Desmos, but that's what we had for W, for our width. When my width was 0, my area was 0. When my width was 1,200 feet, my area was also 0. The max here is occurring, because this is a parabola opening down, the max occurs at the vertex. So when the width is 600, the absolute max area is 720,000 square feet. Okay, so this concludes this video. In the next 2 videos, or maybe I'll do it in one, we're gonna talk about, well, what if you didn't really get the area, get the domain here? Could you use the first or second derivative test to talk about how to find an absolute max or min? And yes, we can. You got to be a little careful, but let's go ahead and do that next.